So we've talked about the subset relation, what it means for one set to be a subset of another, but there's other ways that sets can be related to each other. And so in this section, we'll talk about set operations. If A, for example, is a set containing the elements 1, 2, 3, 4, 5, B is a set containing 4, 5, 6, 7, 8, then we can represent the relationship between A and B using a Venn diagram, and it's useful to do so because note that A is not a subset of B here, because, for example, A contains the element 1, which B does not, and B is not a subset of A either. B contains 8 and A does not. So it's useful to represent the relationship with the Venn diagram, which is just a diagram that shows how these sets are related. We can list all the elements in exactly one spot in the diagram. We're going to put 4 and 5 in this overlapping section in the center of the diagram, right here, because these are the elements that appear in sets A and in set B. But the elements in A that do not appear in B, 1, 2, and 3, should be on just the left-hand side of the circle, and similarly 6, 7, and 8 will appear just on the right-hand side of the circle. We usually do a Venn diagram inside some sort of a larger circle or box to represent a universe or a universal set. This is just some set that contains everything that's in A or B or both, possibly with extra elements as well. So if our universal set is n, the set of natural numbers, then out here in the box we have all of the natural numbers that are not in A or in B. So we would have 9 out here, we'd have 10 out here, we'd have 11 out here, etc. Okay? If your universal set was the integers, then we would also have a 0 out there, and a -1 and a -2, etc. So there's infinitely many elements that are out in that universal set box. We see that the union of two sets A and B, which we denote A with a U symbol, B, is a set of all elements that are in either A or B. So in set builder notation, we would say A union B is a set of all X in our universal set. U is the universe here, such that X is an element of A or X is an element of B. Okay. On the other hand, the intersection of two sets A and B, which we denote A with an upside down U, A intersect B, is a set of all elements that appear in both sets, A and B. So this is a set of all X in our universe such that X is an element of both A and an element of B. So in our example from the last page, the union of these two sets is a set of all elements that appear in at least one of the sets A and B, or possibly both, right? This or is an inclusive or, so we'll include the case that X falls into both sets. So if we list out everything that appears in both sets, we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9. So essentially, A union B is everything that's in A or in B. We get this whole thing right here. On the other hand, let me just take that away, A intersect B is the stuff that happens to be in both sets. All right, well, the only elements that fall into both of these sets are the things that are in the overlapping part, right? This football shape in the middle. So that would just be the set containing 4 and 5. You can find it here in the Venn diagram. Okay. Note that the union in the intersection of sets is itself a set. So when we're describing the elements of the union or the intersection, you should put curly brackets around it. One more definition here. We say that two sets are disjoint if they have no elements in common. That is, if their intersection is equal to the empty set. So just to give you an example, if we let C be the set 2, 4, 6, and we let D be the set containing 1, 3, and 5, well, the intersection of these two sets, the elements that appear in both of these sets, is nothing, right? They have no elements in common, so we would say that since the intersection of these sets is equal to the empty set, C and D are disjoint. Okay, so a couple of examples. If we wanted to intersect the set of integers with a set of natural numbers, we can't really just list all these out or draw one Venn diagram because these are infinite sets and we can't list all of them. So we need to think to ourselves, what are the set of elements that are both integers and also natural numbers? Well, 1 would certainly fall into both of these sets. 2 would fall into both of these sets. In fact, you end up getting all of your positive whole numbers. And note that that's actually equal to the set of natural numbers. Now, in the second case, if we wanted to union together the integers with the natural numbers, we just want to kind of glom everything in together into one big set. So we get all of our integers, all of our positive and negative whole numbers in 0, along with all of our natural numbers, except these natural numbers are already sort of wrapped up in the integers. So we don't really get anything new here. We get 0, plus or minus 1, plus or minus 2, etc. So we end up getting the integers back again. Well, notice that the reason that this happened is that the natural numbers was a subset of the integers. So when we intersected them, we just ended up with the first set. When we unioned them, we ended up with the second set. And we'll show in the exercises that this is true in general, that if A is a subset of B, then the union of A and B, let's start with the intersection. The intersection of A and B is just going to be that smaller set A, and the union of A and B is going to give you the larger set B. Of course, if the sets are equal, then that'll be equal to, A will be equal to B as well, but this will still be true. We'll prove this in the exercises. Just a couple of more definitions. The difference between two sets, A and B, which we denote A minus B, or sometimes we denote it A backslash B. You'll see this in the web work sometimes or in other textbooks that they'll use this notation interchangeably. It's just a set of elements that are in the first set but not the second. So the elements that are in A but not in B. So we would write this as A minus B is a set of all x, such that x is an element of A but not an element of B. So if we go down here and look at our Venn diagram, if we want the set A minus B, we want the stuff that's in A but not in B. So we want the stuff that's not in the intersection. So essentially what we want is this right here. In this example, A minus B would be the set containing 1, 2, and 3. We could, if we wanted to, also define B minus A similarly. This is going to be the set of all elements of B that are not in A. So we're going to want the stuff that's in the B circle that's not in the A circle. So we want this. We'll end up with 6, 7, and 8 is B minus A. All right. And our last definition, if U is some universal set and A is a subset of U, we define, whoops, I probably should have written the word here. We define the complement of A to be the set of all x such that x is in our universe and x is not in A. So essentially, just throw out everything in A and see what's left over. All right, so notationally we use this notation of A with a bar on top, or sometimes you'll see A with a superscript of a C. Again, these are both very common notations, so I'm showing you both. Just be aware that it means the same thing. So in our example here, we had said that, or we had defined our universal set to be the natural numbers. So remember that within this box, we also have all of the natural numbers that aren't in A or B. So we had 9 out here, 10, 11, etc. So if we wanted to define something like a complement, well, we want everything in the universe. A complement is going to be everything in the universe. So everything that's a natural number, such that x is not an element of A. In other words, we want to take everything outside of A. That's going to be our A complement. Some of that stuff's going to be in B as well. Some of that stuff's not going to be in B. But in particular, you just get everything outside of the A circle. So you get every natural number except 1, 2, 3, 4, and 5. Okay, so we would get 6, we get 7, 8, 9, 10. And at this point, I'm just going to use ellipses, ... to express the fact that we don't want that. We don't, or that we will continue infinitely after this point. Another way of writing this is we could say, well, this is just a set of all natural numbers, but we want to take away everything in A. So it's the entire universe minus the stuff that's in A, using that set difference notation from up above. Okay? Similarly, if we wanted to find B complement, well, we want everything in the universe except for the elements of B. So if we take everything in the universe, but we take away the elements of B, take away 4, 5, 6, 7, and 8, we're going to be left with 1, 2, and 3, and then 9, 10, 11, etc. Right, so B complement would also be an infinite set in this case.